Welcome to MADIA's February meeting at SiLC Technologies. Thank the host for inviting, for allowing us to be here. It's a great location. And just briefly on MADIA, we're a 501c3 nonprofit educational organization. Our mission is to ensure that technical, scientific, and industrial workforce have the tools they need to do entrepreneurship and commercialization and finance and development of technology, and to make sure they come together and collaborate. With that, I will introduce our presenter, who is Dr. Bahram Jalali. He is the Distinguished Professor Emeritus of Engineering at UCLA and a top 10 author in Nature Photonics. He is the first person to be inducted into the National Academy of Engineering for his work in silicon photonics. He was the founder and CEO of Cognet Microsystems, a pioneering CMOS optical IC company acquired by Intel. The second company spun off to commercialize his research was acquired by BD Biosciences in 2017. His silicon photonics work has been recognized in the Scientific American Top 50 and MIT Technology Review Top 10, and he has received the Optica R.W. Wood Prize and the IEEE Kressel Award, among others. Bahram began his career at the Physics Research Division of Bell Laboratories in Murray Hill, New Jersey, after completing his Ph.D. in applied physics at Columbia University. And he has more than 70 U.S. patents, and somehow with all that, he is an avid sailor as well. So please welcome Dr. Jalali.
Do I need a microphone or something?
Okay.
Thank you, Bruce. All that means is that I'm old. That's what it means. But I'm your dinner entertainment. So happy to be here. Thank you, Bruce, for the invitation, organizing this, and thank you, Mehdi and the SiLC team for hosting this. So we're going to talk about the technology that's in the news a lot these days. It's almost impossible not to, open up CNBC and Bloomberg News and not to hear about silicon photonics. And there's no other better place to talk about silicon photonics than here, because SiLC is the world leader in silicon photonics, and it's used in LiDAR for autonomous driving, drone detection, and so forth. So I hope the microphone is working, because the background noise is quite a little bit high. But
we can hear okay? Okay. So everybody get there?
There's a there's a humming noise coming from here. That AC. Right about it. Anyhow, I will scream until my voice stops. So yeah, so let's get started. So the title, Bruce and I were going back and forth. There were two separate titles that appear, but anyhow, the topic is talking about silicon photonics. Now, what is silicon photonics? I realize we have high school students here. So let's just start with the very basics. So what is photonics? Photonics is the science and technology of dealing with light and using light for different purposes, for communication, sending data from point A to point B, for doing sensing in a non-contact manner, and for such as LiDAR, and for making biomedical sensors and so forth. So traditional photonics looks like this on the left side here. You have lasers. This looks like a gas laser here. And then the light goes through free space. And because light, when it propagates through free space, it diffracts, it diverges. You need lenses to manage that, to keep it focused. So a typical photonic, old-fashioned photonic system has lenses. And to bend light, you need, I think I should go on these.
You were coming through there, but that was it.
Sorry, yeah, but I can.
Well, the slides.
Yeah, it could be. That could be. So, to bend light, you need mirrors to bend light. Now, Silicon photonics tries to do everything on a chip and make use of the silicon or semiconductors vast manufacturing infrastructure. And the idea is that you make these what's called ridge waveguides. These are just dielectrics in which light gets trapped and propagates along those waveguides. So they act like wires, except instead of electrons, you have light going through it. Because of that, you can bend them easily without needing mirrors, and you can also create sophisticated optical circuits. You can create structures like this, which take two beams and interfere them together to do interesting functions. You can make what's called resonators, these circular donut-shaped things here. And then you could put electrodes, metallic electrodes here, apply voltage and change the optical properties of that waveguide, and you can change what light does when it comes out. So this is what we call silicon photonics. You take optical or photonic systems like this and put them on a chip so you can make many of them, make sophisticated circuits at low cost, low power, and so forth, all utilizing the silicon semiconductor industry. By the way, if any questions, please ask me anytime. So this is a very important moment in the history of this industry. The 2026 shapes up to be a watershed moment for this technology, because this technology is coming out of obscurity, and the market size is beginning to be sizable to an extent where the size of the silicon photonics market is appreciable or appears on a radar screen of the entire semiconductor industry. So this is a big moment, and a good amount of the theme of tonight's talk is to talk about why that is the case. So we talked about Bloomberg News and CNBC and finance and so forth. So this is what's important to note here, in that this industry, the growth rate for this industry is very high. The growth rate of 25 to 30% a year. So for our high school students who benchmark that, if you put your money in the bank account, you gain maybe 1% a year. So this is a huge growth rate. We all wish we had such growth rate, 25 to 30% a year. We get rich very quickly. And the key drivers for this large growth is the emergence of AI and the AI infrastructure, data centers, and what goes inside these data centers that are being built at very fast rates. These data centers require links that connect the GPUs and servers together with a very high bandwidth, 400 gigabit per second and 800 gigabit per second and more. And all of these, you cannot do these kind of data transmission using copper cables. You need optical fibers and light and photons. Yes.
Is there a lag in silicon photonics chip development, given the huge backlog of GPU development for general AI and other types of chip?
Yeah, very good question. So yes, indeed, as we'll see, some of the biggest champions of this are the GPU companies like NVIDIA. Yeah, in fact, the industry would not be where it is if it wasn't for those guys. So, if we just look at the last few months, from October till now, there's been some major announcements of merger and acquisitions in this industry. And when mergers happen, that means that people who are buying the companies are expecting a lot of profit and huge revenues. So Global Foundries, which is one of the major silicon semiconductor manufacturers, just bought AMF, Advanced Micro Foundry in Singapore. NVIDIA announced two new optical switches, so-called Spectrum X. And then Marvell, which is another major semiconductor company, just spent several $1 billion acquiring a company called Celestial AI in December, just a month ago. So a lot of money is being exchanged, and our mission tonight is kind of unpack that and see at the technology level, at the photon level, why is that? Why are these companies spending billions of dollars on this? So now the mysterious thing, puzzling thing is that silicon photonics is not a new technology. Okay, so a few months ago, last year, I was asked to speak about it at a conference called CLIO, which is a optics conference every year, and they had a session on silicon photonics and all the new stuff. And so I put up this slide. This is 1992 at the same conference, where I was talking about silicon photonics, making photodetectors using silicon material that can detect light at the wavelengths that are good for communication at longer wavelengths that silicon is not able to detect those things. And this is not new, but in those days things were different. To kind of give you an idea how difficult it was to do things in those days, because there was no ecosystem, right? But this was a birth of the technology of the industry. So this project, which was published in 1992, actually started in 1989, right? To make these material that can detect light at these wavelengths on a silicon substrate, so-called silicon germanium. I had to design a chemical vapor deposition, so-called reactor, to grow that kind of crystal, and I had to work with a company in Silicon Valley called Rapro to design that system and manufacture that system and ship it on an 18-wheel truck, which was with air shocks, because you couldn't afford damage, from Silicon Valley to Monrovia, New Jersey. And getting it installed in my lab took about a year of building the infrastructure, the power supplies. These things deal with very nasty gases, toxic explosive gases. So building the gas safety infrastructure, gas purification systems, the exhaust systems that can get rid of the exhaust fumes and stuff like that. So, being early is good, but not so good, because there's no infrastructure to rely on. I had to figure out how to make the crystals and then make devices and so forth. And here, this is a figure from the paper. This is a fiber with a micro lens at the end. And I was even making my own micro lens fibers by suspending an optical fiber in a beaker of hydrofluoric acid under the hood to do these things. So yeah, so the bottom line is this technology is not very new. It's been around 35 years or so. So what has changed? So to give these young people how many years ago was 1992, here's a quiz. So can name these two characters. So that's Bill Clinton, and then his vice president, Al Gore.
The inventor of the internet.
And who claims he invented it.
UCLA. Yeah, with UCLA.
It is. And who are these people? These are the rock stars of the time. Madonna, Freddie Mercury.
You're the all-stars.
Michael Jackson. And then what's his name? George Michael. 1992 was also the year. Yes.
What were these four things? Mention that's like four companies spending billions on it now. Like when you use the peripheral impulse,
Nothing. Well, this is curiosity. Photonics was being done in more exotic material, indium phosphide and gallium arsenide and things like that. And I was lucky. I was at Bell Labs. Bell Labs created this whole industry, photonics industry. But silicon was used for making electronics, for making microprocessors and memory for mainframe computers. It was early days of PCs. But it was a curiosity, can we do photonics in silicon? Because silicon is cheaper. At the time, it was considered just easier material to work with. But this is also the year I moved to California, to LA from New York City, and this is what I walked into. So in that time, we had the LA riots and the looting and the fires and so forth. For me, it wasn't a big deal because I came from, I was living in Morningside Heights in Manhattan. Columbia University is next to Harlem. So these things did not scare me. I think at the time we had New York City, we had 7 homicides a day on the average. So anyhow, so 1992 was a long time. But what changed since then? What changed and why all these billions of dollars are changing hands is the generative AI boom, the so-called ChatGPT moment, right? This has fueled a massive amount of building, just construction, building these massive campus-sized data centers. The big tech companies, the Magnificent Seven, Microsoft, the Google, and so forth. They have announced that they're going to be spending north of $650 billion this year on building these data centers, right? And this is just the U.S. big Mag 7. If you include the Alibaba, Tencent, and other players, the total amount of money being invested this year is over $1 trillion. Okay? So that's what has changed. We didn't have this in 1992. So as a result, now you have an entire ecosystem. Like in 1992, there was no ecosystem, right? You had to do everything yourself, make the material, develop the process to fabricate things, measure them, test them, and model them, and things like that. Now you have an entire ecosystem of designers of these silicon photonic circuits, makers of the substrate, the wafers, makers of the layers of material that you need on top of it, and everything in between. Yeah. So why all this investment? The reason is because these are generative AI models that you all enjoy, ChatGPT, Gemini, and so forth. We can talk to it. I say professors like me are obsolete because before, let's say you had a question about some advanced laser physics, you had to make an appointment with the professor, deal with the traffic, go to campus, pay for parking, and then go talk to the professor to ask a question. Now you could be sitting, in front of your TV on your couch, and you could ask ChatGPT the same, get answers to the same questions. So these generative AI models are completely changing the world. All the intelligence is not for free. They come because these models have a lot of parameters, free parameters. Okay? The latest models have over 1 trillion parameters. Okay? And to train these models, it's like, imagine you have an equation with 1 trillion variables, and you have to fit those variables to your data. Right? It's unimaginable, but that's what's happening here. They're able to learn everything. But all of these comes at a cost. You can no longer do these things on a single processor, like CPU or GPU. You need many, many of these things tied together to form a single massive computer to learn the behavior of the data, and then also to be able to answer questions, so-called inference stage. So all of these GPUs, hundreds of thousands or millions of them, need to be interconnected. And the bottleneck that has emerged is the interconnection. To do that, you need switches. You need switches to connect all these things at different layers to create this massive computer made up of small computers. So if you look at these so-called GPU clusters, massive clusters of processors, they rely heavily on interconnects. And because the data rate in these interconnects is so high, 400 gig, 800 gig, 1.6 tera, you have to use optics, so photons, if you go more than a few meters away. So you can see one example of these architectures. You have this one server, you have several GPUs, you have a CPU and memory, and then now you want to tie them all together. So you need networking. And these clusters are getting so big that now you are talking about clusters that span not just one building, but multiple buildings and multiple sites. So this is an example of the modern data centers, those construction pictures that you saw, that ties the GPUs in the different buildings within a region, within a site, and then combines that, ties it to GPUs in another site, another region. And so networking is becoming the key to enabling generative AI, ChatGPT, Gemini, and so forth. And that's where silicon photonics comes in. So, imagine you're trying to make all of these processors behave like a single computer, right? So you need very high bandwidth interconnection between these things. And also latency, the delay has to be very, very low, right? Because they all have to act as a single computer, right? So several years ago, there was a curious acquisition. Microsoft bought a company in Southampton, UK. And there wasn't much news about the acquisition. The company, they had a unique technology. They have what's called hollow core fiber. So these are optical fibers, but the core of it, instead of being a strand of glass, it's actually air. It's hollow. So light travels in air, right? And the reason Microsoft bought it, because light traveling through air goes 50% faster than light going through the glass. So the latency gets cut down by 50%. Right? It's a big deal. What's the point? But 50% over kilometers, that adds up to significant microseconds, milliseconds of delay. And this is why Microsoft bought that company, because they were anticipating that they have to build these massive data centers or data center campuses, and the latency between the interconnects has to be so low that they have to make them behave like a single computer. So the interconnect is becoming the wall, and unfortunately, fortunately for us, because we solved that problem, so it's good that there's a problem. Interconnect is a delay. Essentially, the interconnect performance scaling has not kept up with the processing, digital logic processing. So the gray here shows the performance increase of the processors, GPUs, CPUs, TPUs, and so forth on a log scale. And these curves show the performance of the interconnect and also the memory. These models require massive amount of memory, and you cannot put all that memory in one place. You have to distribute it, and then you need interconnect between them. So the industry of the AI industry has hit a wall, memory wall and interconnect wall, and that's what silicon photonics and people like us can solve. So now unpacking that, getting into the under the hood, why is there an interconnect limit? So optical switches switch packets between different inputs and outputs, and they're connected together with optical fibers. At the edge of the switch, you have what's called an optical transceiver, which converts light coming in from a fiber into electrical signals that go on a printed circuit board and get switched by the electronic switches. So inside these switches, it looks like this. So you have the main switch chip that switches the packets. This is the digital silicon chip. And then this is sitting on a printed circuit board, PCB. On the edge of it, you have one of these so-called transceivers. They get plugged into the edge. They take data in the form of light coming into the fiber, convert it to electronics, that then goes to the traces on the PCB, goes to the ASIC switch. because the data rates are so high, the interconnection from here to here is an issue. So to correct for the impairments or the distortions that are caused by the metal traces on the PCB, you have to do a lot of digital processing, DSP. And this is causing, this consumes a lot of power. And this limits how many of these things you can have in a big switch and in a big data center. So the relative power consumed by this DSP keeps going up as the data rate is going up. And this is contributing to that wall. So why silicon photonics is gaining so much interest? But this is just another more detailed explanation of that effect. But anyhow, so the idea is the following. The idea is that instead of putting the optics to electronic converter at the edge of the switch, you put it right next to the silicon chip. Okay? So you bring the fiber all the way onto the PCB. Okay? So you reduce the distance that the signal has to travel to the electronic wires. I know this is getting boring probably to high school students, where is Madonna and Michael Jackson? But for us techies, this is actually more exciting than rock and roll. I see Cedric there is jumping out of his skin. Really exciting. But anyhow, this is equally exciting, and actually is, believe it or not, there's more money exchanging hands because of this and because of
It's about communication costs either way, right?
that's right. And so you're putting the optics close to the chip, and to do this, you need to integrate the optics with the electronics, on the same chip, or using a similar platform. So in a nutshell, this is what's happening. So we need to make optics very, very small to put it very, very close to the silicon logic chip. And this is called CPO. So you hear this a lot in news these days, CPO. All the companies are claiming they're doing CPO. It's called co-packaged optics because you package the optics in the same package as electronics together. Okay, CPO. This is why you need silicon photonics. So you can see here, this is a switch. These are the ports, the channels of ports coming into the switch. This is the switch that does the switching. So it takes the data from one and switches it to the destination and another port. And here, the idea is that the fiber is coming onto the box, and it's actually going right onto the same substrate at which the silicon switch is sitting. So you need very, very tiny optics integrated very, very close to the chip. And therefore, you need silicon photonics.
Obviously, you can't do computing with light. You have to switch to electricity.
Yes, you cannot do computing with light. There are lots of scientific papers that show very crude examples of computing with light, but it's a long way from being able to do the needed processing.
How big was on that previous slide is that thing on the right?
This thing here?
Physically, could it be as big as my hand?
The chip or the transceiver?
Whichever.
So this transceiver is about maybe inch and a half or two long. Okay?
Smaller than a thumb.
Yeah, and this ASIC is about maybe a centimeter, 2 centimeters, 2 centimeters.
Okay.
There are examples of it in cabin.
Oh, okay, great.
But the point that there are thousands of fibers coming in, okay, and they have to all get inside that chip, get switched to the other port, right? So it's like having an airport, the size of this room here. You have to have 1,000 gates. With all those gates, so passengers can come fit here, right?
How do they QC that thing?
I'm sorry?
How do they QC that thing?
Quality.
Quality control. It's a good point, but once you can make optics using silicon process, the manufacturability, yield, and quality is much, much higher than optics, using free space lasers and lenses and things like that. So that's another motivation for doing optics and silicon. So one question is, where should the laser be? You need a light source to send data with. So there are various schools of thought here. Academics folks, they like to publish papers, so they like always the coolest, fanciest, more exotic thing. So they say lasers should be integrated on the same chip, so forth. You can talk to people in the industry, they say, over my dead body. The reason is because in this system, the first thing that fails usually is the laser. Right? And they have people to, change it without taking apart the whole system, right? So they like the laser to be external and separate from all that sophistication, right? So when the laser dies, you just plug it out, pull it out, and put it in the laser, right? So currently, what NVIDIA and others are doing, the laser is actually sitting just outside. Because you can replace it easy without throwing away the entire module. So when the industry has taken off, when the whales, the giants in the field, are getting into this act. TSMC is the world's largest silicon foundry. They make the most sophisticated chips. So 90% of the GPUs that go in the data centers, the chips in your telephone, and so forth, they all are made by TSMC. It's a company in Taiwan, and they have the most sophisticated processing. And TSMC, several years ago, developed a technology which they call COUPE. And this technology essentially combines the electronic ICs that they're very good at with photonic integrated circuits, PICs. It's a two-chip solution, and they're bonded together. So you can add photonic functionality to the electronic switch matrix very, very close to each other. Notice that the photonics is still in a different chip than the electronics. I'll come back to that later. But nevertheless, they're both made by the same foundry. They're both made by silicon. Typically, the photonic chip is made in older technologies, so about 65 nanometers or so, and the electronics is made in the state-of-the-art 2-3 nanometers. We'll come back to that. And then they're saying that by putting the photonics so close to the electronic chip, we get significant power savings, so 50% power saving. And this is huge because one of the big headaches in data centers is the amount of power that's consumed by the electronics and by the photonic modules. So this is huge. However, when TSMC announced this in 2021, hardly anybody paid attention. There was basically no interest. What changed again was the emergence of the ChatGPT movement, the emergence of generative AI. So for those more techies in the audience, so this is a roadmap that TSMC has. They have already integrated the photonic chips, the yellow silicon photonic chips on the same substrate, very, very close to the electronic chip. And the next version, they're going to integrate high bandwidth memory because those AI models, you have to store those trillion parameters. We call them, put them back, we call them shaded memory, very close to the processor. So integration of the processors, the memory, and the photonics all in the same chip.
So, and when are they expecting to have that fantastic chip done?
How far away is the next gen?
No, I'm going to show you. So this is already in production by NVIDIA, and then this is thing NVIDIA has already shown some examples. Yeah. So speaking of NVIDIA, the devil. So so TSMC has the patent. This is actually from the patent here. Yeah.
Now, do you guys find noise between the electrical component and the photonic component? Like, does electronics cause any mishap with the data coming in from the photonic?
Not so much noise, noise in photonics is larger than noise in electronics. Noise happens because of the fluctuations in the energy being transferred. So the unit, the quantum or the clump of energy in physics is proportional to the frequency of that wave, right? So in electronics, the frequencies are, gigahertz and things like that. So in optics, the frequencies are hundreds of terahertz.
Oh, wow.
So the corresponding, quantum of energy lumpiness is much bigger in photonics than electronics, and therefore the fluctuation of the noise is much bigger in photonics. What electronics does create a problem is the heating. Right? It gets very hot, and photonic devices don't like hot environment. Well, electronic doesn't either, but
Just for those that hope to understand someday, what do you major in? If you want to do this to become an electrical engineer, is that the pathway to photonics, or is it a separate field or separate?
no, photonics is primarily being taught and research in engineering, in electrical engineering departments.
Okay.
Some schools, they have the entire school for photonics outside, like University of Arizona in Tucson, Rochester in upstate New York. They have the entire college of optics and photonics.
So you end up with what degree do you end up with, optical engineering or something like that, or
Well, if you
photonics engineering?
Seju's degree is in electrical engineering.
I was an electrical engineering at UCLA in the photonics laboratory. Just added that.
Professor Monticelli.
Teach laser technology at Pasadena City College. We have a lot of hands-on skills that are involved in this technology.
Yeah.
Can you go back to the previous slide with the, can we, at least for the sake of the high school students, can we give something to scale? You take a look at that, it says 12.8 terabits per second. Right?
Yeah.
So in relation to, let's say, your giggle fiber broadband.
Right. Yeah, very good. But so to benchmark this, so most of us at our home now we get 1 gigabit per second connectivity, and that's more than enough.
So I guess you could say 12 terabit would be like the entire internet times like maybe times 3 or 2.
That's right. In fact, if you listen to Jensen Huang's presentation, he talks about the data rate inside one of his computers is more than the data rate the entire internet. Right?
Watching the reasons shows on Google.
That's right. That's right.
That makes you happy.
And again,
Simultaneously.
the reason is because these models have trillions of parameters. All these parameters have to be saved, recalled, processed, put back on the memory, and so forth.
I do have a question. Do you think we'll ever see like a time where the PIC will take over the EIC? The PIC will take over the EIC?
No, I don't think so, because EIC does a switching. So in switching, you have to be able to switch one thing with something else. Those two things have to interact. Electronics is very good for that because electrons have charge, a Coulomb charge, so one affects the other. Photons don't have charge, right? So one photon doesn't impact the other photons. They can go across each other right through. So you cannot control photons with photons very easily. You have to change the material. One photon has to change the material, and then the other photon sees the effect of that indirectly. That's a much, much weaker effect than direct Coulomb interaction. So for decades, even when I was a student, lots of people working on photonic computers and photonic transistors and stuff like that. That has not materialized because you're going up against physics. Photons don't have Coulomb charge. So NVIDIA recently, a few months ago, they announced these chips. These chips use the so-called co-packaged optics CPU that we just looked at, and they're able to process 1.6 terabit per second of data, switch data. Imagine an airport where people are coming from this gate and going that gate. at the rate of 1.6 trillion people a second. Kind of gives you scale. And this is using TSMC's COUPE process, the integration of EIC, electronic IC, and a photonic IC, very close to each other. Okay. There are other key players in case you came here to know which stocks to buy tomorrow.
Do we buy Intel?
So there are other key players. A couple of months ago, Google announced this called TPU clusters, tensor processing units, which is more specialized processor. That GPU is ideal for doing inference of AI, and these things make use of Broadcom switches. So TSMC has their own switches, and then Broadcom is also another leader. So companies to watch. Google obviously is one of the hyperscalers. Broadcom is a company to closely watch, and Broadcom also came out of UCLA.
It's down in Irvine, right?
Yeah. So
the potential jobs in the future, Irvine, Broadcom, everywhere.
Yeah. So Global Foundries. Global Foundries is another major silicon fab, making chips for others. And Global Foundries is actually quite advanced in silicon photonics. They got in very, very early, before there was any major interest. In 2017, I got a call on my phone, and the person said, my name is Sanjay Jha, CEO of Global Foundries. And an investment banker I was talking to, he said, asked questions about silicon photonics. I said, call Jalali. So anyway, he called and we chatted for a while, and he was quite nervous. He said, I have made significant investments in silicon photonics. Is there going to be a market? So they were very, very early, and because of that, they're reaping the benefits right now. The technology is very, very advanced, and they're one of the leaders. So another company to watch. In terms of electronics, they're behind TSMC by several generations, but in terms of photonics, they're actually probably even more advanced than TSMC.
What country are they located?
The Global Foundries was made up by pieces. So a big portion of it is IBM's whole semiconductor in upstate New York, East Fishkill, Burlingame, and in Vermont, and so forth. They also acquired other assets. Sergio, what are the other fabs?
There was a lot of Middle Eastern investments because Global Foundries originally came from AMD. AMD's fab became Global Foundries.
That's right.
And AMD acquired ATI, got a lot of money, and they had somehow they get out there. But once that happened, they had to get more money, and they got a lot of money from Middle East. So they do have a fab somewhere in the Middle East as well. But a lot of them are in upstate New York.
Yeah, that's a good point. So they started when AMD decided to get rid of their fab, and then they went and got investments from the Middle East and elsewhere. They started acquiring other fabs. Yes.
Just gonna point you to this. It's less visible.
Okay, relay.
I had a question. Talk about GPUs, right? I guess I'm still trying to understand. So, for instance, I know that my computer has online 64, right? CPU, right? So a GPU, how would that change? What changes?
Oh, the different things. The CPU is for general purpose. You run any program on it. GPU is for doing tensor math. So they don't compete with each other. Okay? So you need CPU for user interface to interact with us and the general purpose stuff. But you offload the serious mathematics to the GPU.
So does it make more about speed?
So when you have heavy duty math, matrix kind of math, which is what AI math is, then you use GPUs. So anyhow, lots of stuff. I think Global Foundries is working with some very exciting startups and so forth, doing really cutting edge stuff. So now silicon photonics, a bit of history, and I caution you, this is history according to me, because I know more about my own work than anybody else's work. But it turns out that a good amount of work, early days of work of silicon photonics came out of and what that I was involved in. But how did silicon photonics started? It started from this technology. So in the late 80s, early 90s, to make electronics faster, a new concept came about in that we can have silicon, but instead of silicon sitting on silicon, which is semiconductive and so transistors coupled to each other and bad things happen, we can put silicon on an insulating substrate. Okay? So there's a lot less coupling between transistors and between transmission lines and so forth. So this technology is called silicon on an insulator, SOI. So you have a silicon wafer, you have a buried oxide layer, insulator, and then you have a thin silicon on top. Now you make your transistors on this substrate, and the insulator provides insulation, isolation between transistors and different parts of the circuit. You can essentially create electronics that runs at much faster speed because the so-called capacitive couplings between things that slow things down, they're minimized. This was championed primarily by IBM. In those days, there were two big gorillas in semiconductors, IBM and Intel. Okay, and IBM started pushing this. And in fact, for any of you old-timer gamers, the Nintendo video games, the old ones, used to use a processor from IBM called PowerPC made on SOI. Right? So this is the foundation of silicon photonics, but it was not developed for photonics. It was developed to make faster game consoles. But with this, you can form these ridges that we talked about, these waveguides that carry light because they're sitting on an insulating substrate. You etch them on the side, you have air on the side, so you can make photonic wires or waveguides. Another big development that happened that enabled silicon photonics was silicon germanium. Back in the late 80s, early 90s, silicon germanium was developed not for photonics, was developed for electronics because it was you could make faster transistors again, faster bipolar transistors. Okay. So the origin of silicon photonics came from electronics, and the two key pieces of this were done to make electronics better. In terms of history, a very important figure is Richard Saref, which is an old dear friend. And Richard has a key paper published in '87 that shows that you could actually change the optical property of silicon by injecting electrons into it, or depleting electrons into it. So you could change the properties of light, you could make switches and modulators and so forth. So that was a key pivotal moment in silicon photonics, and a lot of the devices are based on ideas he presented in that paper. Now, just to be complete, Richard was not talking about SOI, which is the current standard way to make silicon waveguide and so forth. He was talking about changing the doping concentration and things like that. But nevertheless, this was a key moment. Personally, I started dabbling into this area during my PhD. I was looking at carrier dynamics, physics of carriers, by looking at using silicon photoconductors to understand the so-called Coulomb blocking of carriers. This was funded by IBM. And then later on, this was a piece of work that showed how you could generate terahertz radiation of silicon photodiodes using short pulse irradiation. Many other notable figures in the history of MADIA Gary, who was here. Oh, man, that's really here. MADIA is one of the pioneers of this field. He did his PhD in silicon photonics in the, maybe I don't want to age you, but
You don't get it older than dinosaurs.
but Mehdi was 5 years old when he published that paper. And then Andrew Rickman, who was the founder of SiLC Photonics, and is also an old colleague. He was a key figure. But a very important pivotal moment in the technology was the first DARPA contract. For those of you who know who DARPA is the main government funding agency for advanced science and technology. Okay, so essentially, if you need a lot of money to do, futuristic science technology, you go to DARPA. And I started talking to DARPA around 1994, and this became DARPA's the first project funded by DARPA, and in silicon photonics. And in fact, the proposal was called Advanced Silicon Photonics, and I think this may have been the first use of pointing of that term, silicon photonics. And here, what I was proposing is that we have a silicon chip, which takes light from a fiber. It has these what's called arrayed waveguide grating, waveguide devices that separate different colors of light from each other. We have the silicon germanium photodiodes integrated onto it that convert the light to electricity. And then we have CMOS electronic functionality that can amplify light and process them and so forth. So this was, it turned out at the time, we didn't know it, but this turned out to be a very high impact project. It led, this is 1997 Optical Fiber Communication Conference, publication of this part of it. And then I'll come back to this, but this essentially had impact and seeded several startups. Yes.
Graphic, is that just a signal from the optical fiber or copper?
Here, this is here meant to be single, but you could have an array of these or replicate these and have an array.
So are each of the photo detectors taking a different
color of light? Each of them detects a color channel, so different data channel. So this project turned out to have a lot of impact. So it started in 1995 at UCLA, and the person that deserves a lot of credit is Bob Lehaney. Bob Lehaney was a program manager at DARPA, and at that time nobody was talking about doing optics on silicon. So he took a gamble. He funded the project, and the project was quite impactful. So in '97, we started transferring the technology from UCLA to JPL, to the Micro Devices Lab, which was a indium phosphide compound semiconductor lab. And this is a letter from the director of that lab at JPL to Bob Lehaney at DARPA, thanking for the technology transfer from UCLA to JPL. A fellow named Chi Wu, who was the second in command at JPL lab, he took the technology and spun off a company called Lightcross here in Monterey Park. Okay? And Lightcross was restructured by VCs a few years later. It was renamed Coutura, but in Monterey Park, same facility. Coutura was later Mehdi joined Coutura in I think don't want to age you again, but
20 years ago.
20 years ago. And then Coutura was acquired by Mellanox in 2013, and key figures like MADIA eventually started SiLC. Around '97, we started getting interest from Bookham, which was actually, I think, the first silicon photonics company interested in this. And Bookham and Rickman used to send a couple of his engineers to my lab at UCLA to work with the PhD students and learn how to design these structures. So Bookham became the first company that commercialized that device. The electronics was spun off by myself into a startup called Cognet Microsystems, which was acquired by Intel in 2001. And then one of my students from this project started Silicon Lightwave, which is a company in Irvine. So anyhow, this the first DARPA project, turned out, we didn't know at the time, but turned out to be quite impactful.
So we were at Bookham also, me and Jonathan, before we went to insurance.
I'm sorry?
We were at Bookham before we came to insurance.
That's right.
Yeah.
Yeah. I think that's where we first met.
Yeah.
Yeah. So anyway, this is some of the stuff from my own company that became the first company that could do 10G optical transceiver chips in pure CMOS. This was in 2000, and this is part of the team that got acquired by Intel. Many other things came out. This is some of the milestones that came out for our UCLA lab. It turned out we were able to show that silicon can also amplify light, can also laze. So the first demonstration of lasing in silicon, amplification of silicon came out of the UCLA lab. And then many other first optical amplification in the medium thread, part of the spectrum, which is very important for defense and medical applications, and then so forth. So I know we're coming to an end. Either that or I'm getting tired.
You need a drink.
No, I'm just joking. Us professors, we can talk. Talk to death. So cut me off. If I don't stop talking, pull the plug on the projector. So what might be some future opportunities? So now there's a whole ecosystem, there's big companies, spending money, and great stuff is being done, terabyte per second and so forth. But what might be some opportunities for the future, for the young people? So these switches in data centers, they have a lot of fibers going into them. So fiber density is becoming an issue. So how many gates you can build into the airport, that issue in a small size. So a very interesting development that's been brewing in the last 20 years or so, multi-core fibers. This is a single strand of glass fiber, but instead of having one core inside, has many cores, a multi-core fiber. These are very good for creating high-density interconnects. But right now, the way these are used is that at the beginning and at the end, at the two nodes, you have to separate these fibers coming out, going to individual transceivers. That defeats the purpose because once again, you separate things out, you have a number of gates issue. What would be really cool is if you could build transceivers that are basically 3D, 2D in this direction and the third dimension along the length. Then we could truly take advantage of the density that's is offered by these technology. So for that, we also need some way to integrate optics and electronics very densely together in a small package. So silicon photonics would be a great platform for doing this. Another opportunity is the emerging what's called AI RAN. RAN stands for Radio Access Network, essentially cell phone tower system. Okay? And right now, cell phone towers are only used for communication. People like NVIDIA and others are championing putting small data centers at each base station. That's really important because for many applications, you need the real-time feedback or processing by the AI. And you don't have enough time to send it to some data center in Norway, process it, and send the signals back. Imagine you're doing autonomous driving or robotics, flying a drone. You need very, very fast processing. So the data center has to be very close to the user at the edge of the network. So they're talking about essentially having a data center, small data center at the base station of the cellular network. And this can also enhance the communication. You could essentially monitor the spectrum and you can optimize the spectrum usage to make the most efficient use of the spectrum.
How small is this data center you're talking about? The size of the house, the size of the garage, or the size of Costco?
So when it's at a Costco, it will be much smaller because imagine you have a tower, maybe the size of a what you call gold container, smaller, right? So so anyway, imagine having a small micro data center at every base station, right? So to do these things, now these things have optical fibers coming to them. They have microwave, millimeter wave circuits for the radio part of it, and their network. So they need switches and so forth. So you need to integrate the microwave, millimeter wave circuits. You need to integrate optical functions, digital signal processing, switching, and so forth on a common substrate. So silicon photonics would be fantastic for this. So AI RAN is another opportunity, future opportunity for silicon photonics. Here we are, SiLC. SiLC is the leader in LiDAR, making very small, efficient LiDAR that can do 3D imaging and sensing. And this is some results from SiLC showing exceptional performance in LiDAR's ability to detect drones. Drones are a major issue for security because the traditional air defense system relies on long-range radars, in Alaska or in Greenland, looking over the horizon for incoming missiles. With drones could be launched from Costco's roof, the neighborhood, fly very low. So you need a different air defense system. So an emerging concept is called ISAC, Integrated Sensing and Communication, in that we have all these base station towers everywhere, right? They cover, anything that's worth covering, all the cities and areas. They're already sending in radio frequency microwave signals. Why not use them as a radar, right, to look for drones? And we have an entire city, the country covered. And radar is not very good with detecting drones because drones are mostly plastic, they don't reflect radar, and they're small. LiDAR works much better, as SiLC has beautifully shown, right? So why not put LiDAR, and you can also have radar on these cell phone towers, and then now you have an entire integrated air defense system because all of these cell towers are connected together, right, by optical fibers forming a huge network, right? So there's a lot of interest and push by the government to have the telecom carriers integrate sensors like radar, LiDAR, and so forth into these things to provide an air defense system for drones. So same thing here. You need to integrate photonics with microwave millimeter waves, with switching, with intelligence, AI to detect the drone, and so forth, perception, functionality, and so forth. So this is also another potentially very exciting opportunity for silicon photonics, integrate all the functionality necessary to create these ISAC systems. There are also more fundamental problems. So as much as, all the giants are not doing these things, photonics ICs and electronic ICs are still incompatible. Okay? So in 2006, I wrote a paper which apparently was very well read, but I got a lot of criticism and anger because of it, in that I cautioned irrational exuberance, in that I said silicon and photonics and electronics will never be on the same chip. Okay, they can be both made in silicon, but it will never be in the same chip. And the reasons I pointed out was twofold. One was the power consumption. So this is from a slide from a talk I gave at Caltech in 2007. I was highlighting the problem with electronics. Electronic chips run very hot. A state-of-the-art electronic chip is running at about 100 Celsius, right? And can actually cook an egg on it. So,
not recommended, but yeah.
Well, it's free heat.
Set an AI generated image, yes.
Those of you who know laser physics, you know that lasers hate high temperatures because at high temperatures, non-radiative processes become dominant, and the laser efficiency becomes very, very poor. So lasers they behave very poorly at high temperatures. So you definitely don't want to put laser on the chip. And also some of the other devices, the photo detectors become very leaky, thermal generation of electrons and so forth. So this is one reason I pointed out that you don't want to combine them into the same chip, and it's not going to happen. Another one was somebody said here, they said they're a real estate developer. Okay, so you know all about real estate. There's a real estate problem on silicon wafers. When I was at Intel, I learned that the real reason semiconductor companies scale the feature length down from 12 nanometer to 10 nanometer, 2 nanometer, 1 nanometer is really not because of the higher performance. That happens, an afterthought happens as a consequence. The real reason they do that is because they can put more functions per square millimeter of the wafer, right? And they can charge more for it. So the profit margins go up, right? So real estate on the silicon wafer is very, very valuable, right? And you have a size mismatch between photonics and electronics. The photons have wavelengths on the order of a micron, 1,000 nanometers, and can go to half a wavelength to 500 nanometers, a little bit lower, things like that. Electronics, electrons wavelengths are nanometers, right? So we can make electronic devices much, much smaller than photonic devices. And that's just basic physics. Nothing you can do about it. At least not now. Maybe tomorrow, one of you guys will have a brilliant idea. But at least up to now, you have this size mismatch. So you're not the silicon folks who are making 2 nanometer CMOS, they're not going to allow you to put a 10 micron photonic device on the same wafer because it's wasting too much real estate. They want to build high density apartment buildings, not massive mansions. Yeah, so that's the other reason. And so far that has turned out to be true. Remember, TSMC is making silicon photonics, but they're two separate ICs. Right? Photonics is made by a cheaper, older technology, but the real estate is cheaper. The electronic is made by the cutting edge, but the real estate is more expensive. So far, those predictions that genital of anger have held true. But who knows? Tomorrow, one of the young people here might have a good idea to change that. So at UCLA, we were concerned about this, and so we said, what is the way to solve the real estate problem? Is to build a basement. Okay, put photonics, put a garage in the basement, right? The low value stuff in the basement, and put the the expensive units on top. So 3-dimensional photonic integration. Okay, essentially bury the photonics underground, put the electronics on top. Right? So this was not an easy thing to do, and is Prakash here? Prakash Kanat. So Prakash, when he was working in my lab, he was one of the principal contributors to this project. So we created this technology where we implant oxygen into silicon, and then after heating it, we formed SiO2 insulators that so because of that, we can create 2-dimensional light wires and so forth, photonic devices. And to pattern these things in the basement, how do you create valves in the basement? We would implant through a mask. So we'll put a mask that would have openings for the oxygen ions to go through. And then also by controlling the thickness of the mask, we could change the energy of the implant of the oxygen ions. and control how deep they go inside the silicon. So we could create three-dimensional silicon SiO2 structures. Okay. And this is an electron microscope picture that shows, several layers of silicon SiO2 and so forth. And this is a picture. These are so-called ring resonators, which are sitting on a different layer. The waveguides are going the basement. The silicon is on top. And then just to show this is three-layer integrated photonic structures, and to show the concept. Prakash and his colleagues at the lab, they fabricated this device. So here you're looking at the chip from the top. There is this CMOS transistors on top, and underground in the basement there is a micro resonator filter, wavelength filter that's completed in the basement. So this way, the big photonic device is not it's not wasting or utilizing using the valuable real estate on top.
Kind of, you've been up there an hour, so whenever you.
Oh, okay, so I think we're done.
There, the final
So the final frontier, this is not pure, now we get to purely academic, right? You don't hear, Jensen Huang talking about this. Like that's just purely academic. In that silicon photonics talks about, sending data via photons, light to a silicon. What is the limit of that? How much data can I send to a silicon? Okay. So this is something we started questioning, asking a question around 2010. And nobody had, posed this question. Silicon is the most widely studied material on Earth because of its importance. But nobody had asked, how much data can I send to silicon? What is silicon's so-called information capacity? Okay. And information capacity is a very important field in theoretical engineering and applied math. And it was pioneered by Claude Shannon, who was also at Bell Labs, years before I was. But when you talk about information theory in silicon, you're talking about your medium is no longer air or a piece of glass, it's a semiconductor, it's an active medium, has electrons, holes, and carriers and so forth. So this becomes a very, very complicated problem. So we talked about the real estate efficiency. We need to make the devices very small, and to send more data, you need more signal to get actually the signal-to-noise ratio. So you need to send more and more intense light into these things. When you do that in silicon, silicon becomes a sponge at high optical intensity, high optical power, it starts absorbing light. And this creates a lot of problems. And I know I'm over an hour, and you probably don't want to hear about this. But this is really fundamental. This is final frontier. Okay? What we saw is that these processes that happens are unique to semiconductor optical medium. They create not just loss, but they create noise, new kind of noise that don't exist in conventional communication, air, glass fibers, and copper, and things like that. And these noise sources show up, become dominant at light intensity levels or bandwidth levels, at which the loss itself is not visible. So anyway, to cut to the chase, you can come up with an equation that represents the fundamental information capacity of silicon. How many bits per second can I send up to silicon? And you end up with curves like this that to send more and more data, you need to transfer more and more power, the higher SNR. The capacity keeps increasing as you expect, but at some point it peaks and goes down. Okay? So there is a fundamental capacity to silicon, how much information it can transmit. And that's on the order of 10 bits per second per hertz of bandwidth. Okay? So fortunately, we're far away from that. So Jensen Huang doesn't have to worry about this. Right now, the silicon photonics chips are running at about 2 bits per second per hertz. So at 10 we still have a lot of room. But fundamentally, this is going to set the upper limit on what silicon photonics is able to do. Okay, so the final frontier.
There'll be a test in the morning on that.
All the equation, gets to do pizza.
Take the result.
The question didn't look that big, but it took 5 years to come up. So anyhow, so just to summarize, the pizza was good, thank you. And I even had a little bit of white wine, which helped me. But anyhow, so silicon photonics is not necessarily new technology, but it's at a watershed moment. It has reached escape velocity. The market size is becoming comparable to electronics because every electronic switch now needs a silicon photonic chip next to it. All the data centers need these things. So they're very exciting times for you young people. You have a new industry, and for us old people, it's good to see that some of our work is being used. We talked about the new directions, AI RANs, ISEC, and then the problems that are still remaining is real estate efficiency. So our real estate friends can maybe guide us how to solve this problem. And then we talked about photons not having any charge, with how to control them by applying a voltage or with other photons. So that's very much needed in making optical switches and things like that. So that's still a lot of research opportunities in that, coming up with either structures that enhance the interaction or fundamentally new material which require more strong interaction between voltage and light. So on that note, thank you very much, Bruce and Mary.
I think the demos afterwards, I mean, if you look at some of these silver kits, see the little wave guides on them, like they have what they had last time. You can see where this is actually